Hello everybody, welcome to another video of Miss Wallace Teaches Chemistry. I am here with a student, so if you hear her voice, yes, she's here with me. So for this lesson, it's organic chemistry. For this lesson, we're going to understand that carbons form single and double bonds. We're also going to understand the structures of organic carbon compounds in terms of branch chains, unbranched chains, and rings. We're also going to write condense and displayed formula for simple organic compounds, and we're going to understand the term functional group. Now, organic versus inorganic chemistry. When you think about something organic substances, we're really talking about living organisms. And that's what organic chemistry deals with. It deals with compounds that contain carbon, and these carbon compounds are found in living organisms. Sometimes these carbon atoms can be bonded to hydrogen, oxygen, or any other atoms, but the main base of the structure is carbon. So all living organisms will contain carbon compounds. For example, DNA, this has a carbon, it has carbons in it. We also have sugar, which we know C6H12O6, methane, carbon, and ethanol, which is our alcohol. So once again, organic compounds, they have carbons and are found in all living things. Now, inorganic compounds, they usually don't contain carbon, but sometimes they can. So for example, table salt, hydrochloric acid, quartz, and carbon dioxide. Most inorganic compounds are found inside the earth. So for example, hydrochloric acid, it's what we consider as a mineral acid. And table salt, you can obtain table salt from the beach, right? Quartz is another example, and carbon dioxide is found in the air. Know that these were not obtained from living organisms, right? While the organic compounds are obtained from living organisms. Even ethanol is made from glucose, so we can still say that it's obtained from living organisms. Okay, moving on. So the features of carbon. So when you think about carbon, how many electrons does carbon have? How many electrons does carbon have? So carbon, it has carbon C, it has a total of 6 electrons, and so the electronic configuration would be 2, 4. So it has 6 electrons. Electronic configuration is going to be 2, 4. 2 for the first shell, 4 for the second shell. And this question is now asking us, show the covalent bond between two carbon atoms. And it's actually quite simple. So for carbon, when you think about covalent bonding, you're thinking about sharing of electrons, right? So if we draw two carbon atoms, carbon, and we draw the valence shell only for our bond diagrams, valence shell only, using dot and cross, I have 4 crosses for one of the carbon atoms, and 4 dots for the other carbon atom. 3, 4. 4 dots for the other carbon atom. Now when it comes to covalent bonding, how it works is that you're sharing electrons. You're not losing, you're not gaining, you're sharing. So while one is somewhat giving its electron away, it still has the electron. So while this electron is being shared, the electron is still considered to be on the carbon. Make sense? Right. So here I'm going to draw a little back and forth arrow to show that the electron, while it is on carbon number 1, is still on carbon number 2. It's being shared between both. Likewise, this electron here, while it is on carbon number 2, it is also on carbon number 1. So if we were to think about it now, this carbon number 1 currently has 1, 2, 3, 4, 5 electrons. This carbon here has 1, 2, 3, 4, 5 electrons. Remember that this is being shared. Remember that for bonding, the main purpose of bonding is so that the structures can become, or so that the elements can become stable like the noble gases, right? Stable meaning full. They can have a full valence electron. In order for carbon to be full, it needs to have a total number of 8 electrons on its valence shell. We currently have 5, so we need to do another sharing. So I'm going to share between these two. And we would say that this carbon number 1, currently has 6 electrons. 1, 2, 3, 4, 5, 6. Carbon number 2, 1, 2, 3, 4, 5, 6. Still need to do some more sharing because it's still not at 8. So I'm going to share electrons here. Alright, so when I share there, it's going to be 1, 2, 3, 4, 5, 6, 7 for both carbons. We still need to do another sharing. Being shared right there, and now both are full. Note that for covalent bonding, if something needs 4 electrons to be stable, it's going to bond 4 times. If it needs 3 electrons to be stable, it's going to bond 3 times. If it needs 2 electrons to be stable, it's going to bond 2 times. Alright, now for covalent bonding, to complete the bond, we need to draw the Venn diagram. Remember that for ionic, you draw your square brackets. For covalent, you draw your Venn diagram to show the intersection or to show the sharing of electrons. So I'm going to do a little circle here and another circle there to show my intersection. In this case, we had 1, 2, 3, 4 pairs of electrons being shared. So I am going to have one, that's one pair. This is another pair. So I should have 4 pairs of electrons here in the intersection. Now usually on the shell you would draw the electrons that are unbonded or the electrons that were not shared, but in this case all of the carbon electrons would have been involved in some form of sharing, so there would not be any electrons on the shells. And I just write back C, C, and the current electronic configuration is going to be 2, 8 for both of the carbons. Right, so that's it for the covalent bonding. Note that another way we could draw this or write this is C dash, where 1 dash equal 1 electron pair. So it's C dash C, another dash, another dash, and another dash. That's a quadruple bond, right? So that would be how it looks. Remember, 1 dash equal 1 electron pair, 1 dash equal 1 electron pair, and 1 dash equal 2 electrons. Now the next question says show a double bond, and that's something that we need to understand for organic chemistry again. So since I said that 1 dash equals 1 pair of electrons, therefore a double bond, by the way, this is quadruple. A single bond will look like this. So I'm going to just do a dash on X. This would be a single bond that has 1 pair of electrons. A double bond would be something like this, 2 pair of electrons. That's a double bond. Triple bond would look like this, 3 dashes. That's our triple bond. The next question says how many electrons are in each type of bond. So once again, if it's a single bond, it's 1 pair of electrons, which is equal to 2 electrons. If it's a double bond, it's 2 pair of electrons, which is equal to 4 electrons. And if it's a triple bond, it's 3 pairs of electrons, which is equal to 6 electrons. The next question, what does each dash represent? You want to answer this one?
Each dash represents one to two different
atoms. How many electrons are in that dash?
Total?
Any dash. If it's 1 dash, how many electrons?
2.
2 electrons, and we say that's an electron pair. Good. Alright, now we're moving on. Now we're looking at the bonding properties of carbon. So we would have looked at how the structure looks. Now we're going to look at the bonding properties. The first one, the carbon has very unique bonding properties. One of these properties is that the carbon atom is tetravalent. Tetravalent meaning that it has a valency of 4, or it has 4 valence electrons. That's what tetravalent means. Tetravalent, 4 valence electrons. If something were monovalent, it would have had 1 valence electron, but in the case of carbon being in group 4, it is tetravalent. And because of this, when it's bonded to other atoms, the atoms are bonded at a degree of 109.5 degrees. 109.5 degrees. This is not something that you need to know, but it's just a little background. That's the bond angle when they're bonded around carbon due to the fact that it is tetravalent. Once again, I also say that it has a valency of 4 electrons and normally forms covalent bonding or covalent bonds. This right here is an example of methane, CH4. Note that right here we have our, I can't erase, right? So right here we have, let me just draw it so you can see what's really happening. So carbon would have had 4 valence electrons, 1, 2, 3, 4. That's for carbon. Hydrogen would only have 1 valence electron. Now, since hydrogen is only in group 1, it only has 1 shell. Thus, for the first shell, how many electrons do the first shells need? First shell number 1, 2. So shell number 1 needs 2 electrons to be stable, right? 2 electrons, you can have in maximum 2 electrons to be stable. Hydrogen has 1 electron, therefore it would need another for it to be stable, right? So if I were to do the bond between hydrogen and carbon, it's going to be back and forth here. Hydrogen cannot acquire any other bonds. Matter of fact, hydrogen is in fact stable. So what do we do? What do you think we're gonna do? Draw more hydrogen. So I'm gonna draw another hydrogen here with the same electron, 1 electron, and I'm going to share an electron pair. The hydrogen is now stable. This hydrogen is stable, but carbon now has how many electrons?
2.
How much carbon has in all? 4 plus 2, Gil.
6.
You see where we get the 2 from? So it's 1, 2, 3, 4, 5, 6. 6 electrons on the carbon. It still needs 2 electrons to be stable. So I'm going to draw another hydrogen. Draw the dots. Share my electrons back and forth. So this hydrogen is now stable. How many electrons does the carbon have now?
7.
7. Needs another one. Draw my back and forth arrow, and it now has 8, making it full. Now for this structure, we can choose to draw it this way. Know that there would have been an intersection here for the electrons. That's how it looks. That's how they get it. Yes, that's how it looks. Right? And that would have been the Venn diagram. And if we were to include the dashes, you would see that since it goes here, we have 1 pair of electrons here between the carbon and the hydrogen. So it's 1 dash going between the carbon and the hydrogen. For the other one, another dash due to the 1 pair of electron. Other one, another dash, another pair of electron. If it were 2 pairs of electrons, then it would have been something like this, just hypothetically. If it were 2 pairs of electrons between the carbon and the hydrogen, hypothetically. Alright, I'm going to move on. Just remember that carbon is tetravalent. It's able to bond 4 times and it has a valency of 4. The next property of carbon is that it has the ability to catenate, and catenate means that it's able to bond with itself. It's able to bond with itself. Looking at these structures, we have carbon bonding with carbon, forming a single bond with carbon, and it's just continuing. Likewise down here, same for these ring structures here. Now, when you look at it, it says due to the fact that carbon can actually catenate, which means that it can bond with itself, it's able to form straight chain carbons, branch chain carbons, and ring structures, right? And these structures can in fact have single, double, or triple bonds in between them. So carbon can form multiple different types of bonds with itself, right? So catenation, to be able to form bonds with itself. So now we're going to look at the classification based on structure, and the first structure that we're going to look at is the straight chain structure. For a straight chain, carbons can bond with other carbons to form 3 different forms: straight chain, branch chain, and rings. Now for straight chains, looking at it, when you think of, I always use the example of a tree, but this is our tree, this is the stalk, right? This is our tree, this is the stalk. This stalk would only contain, just the stalk alone would just have carbon being bonded to each other. That's our stalk. That's it. So all of these, once it's a part of the stalk, we call it a straight chain, right? There are no carbons coming off the edges of the stalk, so it's a straight chain. These are both straight chain. Note that straight chains can go across, they can go sideways, or they can go down vertically. So it could have looked something like this as well. So straight chains can either be horizontal or vertical. Now for branch chain, when you look at the branch chains, notice that we're seeing the carbons forming a little branch on themselves. So for example, this tree, instead of it just having the stalk with the straight chain carbon, it would have a branch which has another chain of carbon in it. That's how we get into the branch aspect of it. Make sense? Right? So when you think about straight chain, just think about just carbon atoms being bonded to themselves in a straight line versus branch chains, which they in fact have a particular branch of carbon atoms coming off the main chain of carbon. So this would be the main chain, and we have another branch coming off of our main chain. Likewise here, we have a main chain here. It looks straight, but you can see that there's a carbon branch coming off. Right, and it can go sideways, it can go up, down, etc. Now the ring structures, these ring structures, notice that you have cyclopropane. This forms a little triangular ring. It forms a triangular ring. The carbon is bonded to itself while being bonded to other carbons, and it's just go around into a cyclic structure. Likewise for cyclohexane. At this level, you do not need to know it for the CSEC level, but it's a good note. It is a good note to make. Okay, so what we're doing now is that I'm going to show you a little demonstration of the amount of bonds that carbons can have. Now recall that we said that carbons can have 4 bonds. Carbons can bond up to 4 times. Now if I were to draw a structure, right, and it just has 1 carbon atom, note that I could fill it in with 4 other hydrogens. 1, 2, 3, 4. Right, because carbon is able to bond 4 times. Let me do another example. If I had something looking like this, we call it ethane, and they said to fill it in with some hydrogens. Because this carbon is bonded 1 time already, I'm going to have 1, 2, 3 hydrogens surrounding it. Remember that carbon can only have 4 bonds, so it's 1, 2, 3, 4. Likewise to carbon number 2, it's going to be 1, 2, 3, 4. This filling it in with hydrogens. This is once again ethane. Now if I had something like this, note my double bond, and I'm going to draw another one, and my triple, right? And we were asked to fill this in with hydrogens, right? We were asked to fill this in with hydrogens. Now what we're going to do is that for carbon number 1 here, it's already bonded 1 time. So how much more hydrogen would I put around it? 3 hydrogens. So 1, 2, 3. For carbon number 2, it's already bonded 1, 2, 3 times. So how many more hydrogens would I put? 1 hydrogen. For carbon number 3, it has 1, 2, 3 bonds. So how many hydrogens? 1. So we can either choose to put it at the top or at the bottom. Yes. And repulsion happens, but that's another level. For carbon number 4, it has 1, 2, 3, 4 bonds. So how many hydrogens? No hydrogens. Good. For carbon number 5, it has 1, 2, 3 bonds. So how many hydrogens? 1 hydrogen. And this is just a small note before we go into what we're going to do next. Notice that this is already here, so it's not possible. Yeah. If you were to C2 only, then yes. Yes. Okay, this is classification based on saturation. Remember, saturate mean your single bonds. So for organic compounds may be classified according to the type of bonds that they have. Compounds with single bonds in their molecules are called saturated compounds. So single bonds, saturated. I remember a student loves to sing a song. He says, "Saturate me in your single bonds." Yes. So single bonds are saturated, while if it has a compound that contains double bonds between the carbons, double, triple, quadruple bonds between the carbons, we say that it is unsaturated. So saturated means it has single bonds between the carbons, and unsaturated means it has double or triple bonds.
So the bonds in contain
I wouldn't say that, you know. I wouldn't say that. Okay, I see what you're saying. It's just that based on the saturation, the fact that alkanes are saturated, then they're not able to perform as many bonds as alkenes, which are unsaturated. That's just the thing. So alkenes are more reactive due to their unsaturated property. This double bond can break. So this double bond can break in an alkene. Right. Yes. So saturated compounds, they don't usually have many reactions that they can undergo. Just because they're saturated, they already have enough single bonds, they can't really do much outside of that. Now we're going to look at molecular formula, structural formula, and empirical, condensed, and also general formula. Now, the different types of formula. For empirical formula, this is the simplest whole number ratio of elements in a compound. Simplest whole number ratio of elements in a compound. While molecular formula tells you the exact number of atoms present in a compound. So for example, we have a glucose here. Glucose, as we know it, is C6H12O6. Glucose will always have 6 carbons, 12 hydrogens, and 6 oxygens. If we were supposed to simplify glucose, so if I were supposed to simplify glucose using the highest common factor, which is 6, 6 into 6, 1, 6 into 12, 2 times, and 6 into 6 goes 1 time. So therefore, my simplest or my simplified form of glucose is going to be C1H12H2 O1, which can also be written as CH2O. Because in chemistry we have the invisible one, we don't really write the one, so this is how it is correctly written. Just remember that molecular formula tells you the exact number of atoms present in a compound, while empirical formula only tells you the amount of, it only is the simplest whole number ratio of atoms in the compound. Then these are just some examples. So molecular formula of carbon dioxide is CO2. We can't simplify it anymore, so the empirical formula will also be CO2. The molecular formula of water is H2O. Same for the empirical formula, it cannot be simplified any further. The molecular formula of nitrogen is N2O4. N2O4 simplified is going to be NO2. Molecular formula of P4O10. This is the molecular formula of P4O10. Simplified is going to be P2O5. So 2 into 2 goes 1. 2 into 10 goes 5. 2 into 4 goes 2. You didn't realize that? Wow. Okay, so 2 into 4 goes 2 times. Let me see if I'm not get the same thing. 2 into 4 goes 2 times. Alright, then we have C10H2N simplified. We can use 2. 2 into 10 goes 5, and 2 into 22 goes 11. Then C6H18O3. Highest common factor would be 3. 3 into 6 goes 2. 3 into 18 goes 6. And 3 into 3 goes 1. Yes?
Regarding this one, is it like formula for compound? Because this looks like a bit like
Nitrogen dioxide? Yes. Note that you can have one empirical formula that matches for multiple molecular formulas. So this could also lead to N2O4 or another molecular formula, which could also be N3O6. When you simplify both, you would get NO2. Okay, so NO2 would be the empirical formula. These would be the molecular formula for specific compounds. Yes. Now we're looking at structural versus condensed. I'm going to look at the structural formula first. So for structural formula, it's the displayed arrangement of how the atoms are bonded in a compound. It's a displayed arrangement of how the atoms are bonded in a compound. So we already know that this is these are covalent bonds between the hydrogen and the carbon. So we have CH3, carbon being bonded to 3 hydrogens, this carbon bonded to 2 carbons and 2 hydrogens, this carbon bonded to a carbon and 3 hydrogens. Right? So that's the structural formula. It shows you the displayed structural arrangement of the atoms in the bond. Now, condensed formula is when you remove the dashes. When we remove the dashes and we just write it as is. Usually when we're writing the condensed formula, we write it from left to right. So same like how you would read, it's the same way you would read from left to right, so you would write it from left to right. So in the case of this one, the condensed formula, as it says, it shows the atoms bonded to each carbon atom in a molecule, as well as the position of the double or triple bond. It is a shortened form of the structural formula. Now looking at it here, CH3, that's the first one, so we're going to make the carbon the main focus. So it's CH3, carbon bonded to 3 hydrogens. Then we have another carbon bonded to 2 hydrogens. And we have another carbon bonded to 3 hydrogens. So this would be my structural formula of propane. Structural and condensed formula of propane. Let me do another example. Let me just erase this here. Actually, let me keep this. if we were to do the structural formula for this, it's going to be condensed formula, it's going to be CH3. And we're going from left to right, then CH, then CH again, then C, and finally CH. Yes. So that would be our condensed, this would be our structural. Now what if we were given the condensed formula and we're asked to draw the structural formula? So I'm just going to do a condensed formula here. Okay, so this is an example of a condensed formula. What if we're asked to write or to draw the structural formula? So the first carbon has, we have carbon here, the first carbon has 3 hydrogens. 1, 2, 3. The second carbon has 2 hydrogens. 1, 2. And the third carbon, that would have 1 hydrogen. The fourth carbon also has 1 hydrogen. This is where we're at now. It has 1 hydrogen. The fifth carbon has 1 hydrogen. Now note that the brackets, once you see a bracket, it means that there's a branch present. Bracket means branch. So I'm going to draw the branch on the same carbon. This is my branch. And then on the last carbon here, it is CH3. Now when you're asked to draw these structures, I recommend checking to see if all carbons have been bonded enough times. Remember, all carbons would bond 4 times. Note that you cannot add any new atoms, you can only add a bond. You cannot add any new atoms, you can only add a bond. In the case of the first carbon, it's bonding 1, 2, 3, 4 times. This is okay. This carbon 1, 2, 3, 4 times. This one is also okay. This one 1, 2, 3, not. This one 1, 2, 3. This is not. This carbon 1, 2, 3, 4. This one 1, 2, 3, 4. And this 1, 2, 3, 4. So we need to check on these ones. As I said, you cannot add any new atoms, you can only add bonds, right? So in the case of, if I were to put a double bond here, note that it would have been incorrect because it would have made it 1, 2, 3, 4, 5. 5 bonds, and carbon can only accommodate 4 bonds. If I were to put the double bond here, the carbon now has 1, 2, 3, 4 bonds, and that would be correct. Likewise for this carbon 1, 2, 3, 4, that is also now correct. So that's how you would draw your structural formula. Remember that bracket in the condensed formula means that there's a branch group present, and you write it, you draw it and write it based on how you read from left to right. Now going back, this is where we're at. Just remember that structural formulas, they are displayed formulas of the structural arrangement of how the atoms themselves are bonded to each other. While the condensed formula now, you don't really have the dashes present, but you can still have an idea as to where the double bond, the triple bond, the single bond is located. So this is an example. This would be the structural formula. This is condensed. Alright, now here this is asking us to draw the structural formula. So structural is 2 carbons and 6 hydrogen. That is the molecular formula. 2 carbons, 1, 2, 6 hydrogens, 1, 2, 3, 4, 5, 6. 6 hydrogens. Putting my hydrogens on. And therefore the condensed formula is going to be CH3, CH3. That would be my condensed formula. For ethanol, we have 2 carbons, so we're drawing our carbons first, and it says that there are 6 hydrogens present. Now note for ethanol, there's an OH group. That's something that we're going to look at soon. Alcohols have OH groups in them, so I'm going to write my OH group. When I do that, I would have taken away my oxygen, and I now have 5 hydrogens remaining. So I'm going to do the 1, 2, 3, 4, 5 hydrogens. Condensed formula is going to be CH3, CH2, OH. For propane, it would be very similar to ethane. It's going to be 3 carbons with 8 hydrogens around it, and the condensed formula is going to be CH3, CH2, CH3. You can try that one on your own. There we go. Let me just erase all. As I would have said, CH3, with 8 hydrogens, and in our CH3, CH2, CH3 condensed formula. Now, a chemical formula indicates the elements and their proportions in the compound. What that is simply saying is that for every chemical formula, it tells you the amount of atoms of each element present in the compound. The four types that we would have looked at is empirical formula, molecular formula, condensed, and structural. Remember that empirical formula is the simplest whole number ratio of atoms in the compound. Molecular formula tells you the exact number of atoms in the compound. The structural formula is a diagram representation of the bonds of the atoms being bonded to each other. So you're seeing it, it's a structural display of the atoms being bonded to each other. Then condensed formula, it gives you an idea of the single and the double bonds without including the structure, without including the dashes present. Alright, now that's it for this video. In the next video on organic chemistry, we're going to look at the next type of formula, which would be general formula. We're going to also look at homologous series and naming our functional groups, naming our compounds, and so on. Thank you for watching. That's it with Miss Wallace Teaches Chemistry.